welcome everyone to our online NPTEL course Environmental Chemistry and Microbiology. This course will be taught by Professor Sudha Goel and myself Professor Anjali Pal. We both are from Civil Engineering Department of IIT Kharagpur. We have divided this course into two parts. The first part is environmental chemistry that will be taught by me, and the second part is environmental microbiology that will be covered by Professor Sudha Goel. This is my 6th module and 29th lecture, and in my previous modules I have covered acids, bases and salts in the first module. Then in the second module I covered the chemical equilibrium. In the third module I discussed about the chemical kinetics. Then fourth module I discussed about the catalyst and catalytic reactions. In the fifth module I have explained the chlorine chemistry and the nitrogen chemistry, and this is the sixth module where I am covering the radioactivity or nuclear reactions. In my previous lectures I have told you about the fundamentals of radioactivity and the stability of the radio nuclei, why it is unstable, the neutron proton ratio. In this lecture I will cover the following topics. The lecture content is like that: radiocarbon dating, then uses of radiation, uses of isotopes and measurement of radioactivity. Now, radiocarbon dating. In my previous lecture I told you that how the age of a rock or an ore can be determined by using the uranium lead ratio or uranium helium ratio. Here I will tell you also similar thing, but not exactly similar, but very interesting thing I will discuss, and you will see how the carbon 14 can be used for this purpose. Okay. Now, the method was developed by Libby 1945 onwards. They have taken a long time to establish these things. So, that is why this dash is written, and Nobel Prize was given in 1960 to Libby and Libby. This is used for the to know the age of organic material. In the previous one it is the age of ore, but here it is the organic material. What is the organic material? Say for example, it can be wood, it can be hair, it can be skin, it can be some tissues. Okay. So, you can know how old are they. Say for example, some wood, it is produced long time back, say for example, and it is kept say for example for 30 years, 40 years, even more years. So, when it is produced, that you can determine. Now, the method is based on the accurate determination of the ratio of C14 is to C12. I already told you that carbon has 3 isotopes. I already told that carbon 12, this is the natural one, most common, most abundant. Carbon 14, carbon 12, this is the mass atomic mass number, and of course the atomic number is 6, and this is the 14 carbon 14 C, 14, this atomic mass is 14, and there is another, that is 13 C. But 13 C, the question is given here, is 13 C a radioisotope? You already know what is the meaning of radioisotope. So, here it is given that 13 C is radioisotope or not. No, 13 C is not radioisotope, it is also occurring naturally, and with at a very low percentage 1.3% only, and but it is not a radioisotope, it is not radioactive, but carbon 14 is radioactive. Okay, carbon 14 is radioactive. So, this ratio is to be determined, then we can know the how old this what is the age of this organic materials. Okay. Now, I will explain step by step, it is little bit complicated, but very interesting. Okay. What we see here in the outer atmosphere, cosmic rays are there, we all know that cosmic rays are there. So, they produce neutrons with very high energy. Okay. So, in the outer atmosphere cosmic rays produce neutrons with very high energy by collision with air. Okay. So, now these neutrons, you know, they can react with nitrogen 14. Nitrogen 14 is the common one, na? Nitrogen 14. So, nitrogen 14, 14 and 7 of course for nitrogen. So, it reacts, these neutrons that is generated, that reacts with nitrogen. This is naturally occurring, everything is not done in some experiment, okay, in the lab, it is naturally occurring. So, neutron they react with the nitrogen to produce 14C, okay, and proton, okay, according to the equation 1. So, this is the equation. Now, this 14C is radioactive. I told you that 14C is radioactive. Here neutron proton ratio is not, although it is light element, but here the neutron proton ratio is not 1. Okay. 14 is to 14 means here neutron is 14 minus 6. So, 8, okay, 8 is to 6, okay, neutron proton ratio. Now, here this is radioactive. Okay. So, this C14 shows beta activity. What does it mean? That means it radiates the electron, beta activity means electron, as shown in equation 2, okay, and it has T half 57, this is approximately 5760 years. This is the half life, okay, half life of this carbon 14. Okay. So, now what we have seen, initially the neutron is produced by the cosmic rays in the air, in the outer atmosphere, then this neutron reacts with the nitrogen to form carbon 14, okay, carbon 14, which is radioactive, and this carbon 14 produces nitrogen 14 plus beta. Okay. So, this is happening. Okay. You can see here that with beta emission you see 6 to 7, it has increased, it has gone to one position right in the periodic table, okay, that I explained there in previous lectures. Okay. And here you can see 14 plus 1. So, here also 14 plus 1, 7 0, so 6 plus 1. So, it is matching. Okay. Now, this 14 carbon ultimately produces carbon 14 dioxide. So, carbon 14 is produced, but it reacts with oxygen to form carbon dioxide, but that carbon dioxide is C14 carbon dioxide in the atmosphere, and steady state concentration reached to about C14 is to C12, 10 to the power minus 12 is to 1. This is the ratio, concentration ratio, okay. C14 is to C12, this is the ratio 10 to the minus 12 is to 1, so small amount. Okay. Then this carbon 14 dioxide is taken in and given out by plants, because it is mixed condition, carbon 14 carbon dioxide and carbon 12 carbon dioxide, it is mixed. Okay. And so, plant cannot distinguish, plant is taking the mixture. Okay. So, it is both taking out this C14 carbon dioxide and C12 carbon dioxide, and giving out also C14 carbon dioxide and C12 carbon dioxide. Now, the plant eating animals and human beings, means we plant eating human being animal means human being, and any animal also they are eating plants. So, there also this ratio is maintained. Okay. When the plant or animal dies, now the thing is starting when the plant dies, wood is coming from a plant, right. So, when the plant dies, the steady state, this is the steady state is disturbed, since fresh intake of carbon dioxide stops. When a plant dies, then it is not taking any more the carbon dioxide. What is there stored? That is stored. It dies. So, no more carbon dioxide is taken up. Then what will happen? Then radiocarbon dating continued. So, then the 14 carbon continues to decay and 14 carbon is to 12 carbon, that is the ratio drops, because this is then start decaying. This is not decaying, this is decaying. So, the ratio is changing now. Okay, it is no more that 10 to the minus 12 is to 1, now it is changing. So, after certain years only a fraction of it is left. C14 is decaying. So, if you allow it to remain for long time, then after certain period of time you will see that the ratio drops. Okay. And then how much, if you then means measure the ratio present, what is the at present, what is the ratio, you know the earlier one, starting one, you know the ratio, but at present if you can measure by some way the ratio, then you can easily tell that how much time has gone. Okay. That is the theory, that is the means principle behind it, radiocarbon dating. Okay. And this, you know, this Libby and his co-workers could test many archaeological samples and could trace 10,000 years of history. They have examined many samples and huge amount of work they have done. Okay. It is a new principle, right. And then the Nobel Prize in 1960 was given to Libby. Okay. Now, let us do one problem, then you will understand. What is the problem? A sample of wood has been found to contain C14 is to C12, that is 0.8 times as that in living plant. In living plant how much was there? Now it is 0.8 times of that. Okay. What is the approximate time elapsed since the plant died? T half is 5760 years. Okay. So, lambda you can find out 0.693 by T half, that is the lambda, this is the lambda decay constant. Now, ln n0 by n lambda t. Okay. N0 by n, if in the beginning it is n 1, then now it is how much? 0.8 times as that of the initial. So, 1 by 0.8 is equals to lambda t. So, how much is the t? This much years. So, by doing simple experiment you can find out the age of the wood. Okay. It is called radiocarbon dating. Now, we have seen properties of this radioactive elements, okay, and we have seen the properties of the radiations, alpha particles, beta particles, gamma rays, all those things. So, what are the uses of this? There are many uses actually. You know that radioactivity, when the properties and all those things on health also it is not known. That time in Madame Curie's time, Madame Curie died out of cancer, because radioactivity, you know, if you work under this type of conditions, then you will get cancer. Okay. So, it is used for treatment of cancer, but it can produce also cancer. Okay. That is why Madame Curie died out of cancer. That time it was not known that it can cause cancer. Now, what are the different uses of nuclear radiations? Here you see that food, if you keep the food for long period of time, for some time, it will become stale, it will give bad smell. Okay. So, to increase the shelf life of food or water, this type of gamma radiations are used to kill the bacteria. Why the food becomes stale? Because of the formation of growth of bacteria, right. You will learn more during the environmental microbiology classes, but we all know this thing that the food becomes stale because of the microorganisms. So, if you can kill the microorganisms by some way, then it will remain for long time. Now, gamma rays can be used to kill the bacteria and to increase the shelf life. Okay. Synthesis, this is the application. Okay. But milk, pasteurization, that is not done by, that is some other procedure that is used. Okay. But this is used for food or sometimes for water. Now, synthesis of gamaxine. Okay. Gamaxine, gamaxine we are using as pesticide or insecticide. Gamaxine we are using. This is nothing but hexachlorobenzene. Hexachlorobenzene, benzene. Okay. Benzene C6H6, but then there are double bonds, 3 double bonds are there. So, if you can add chlorine, if you remove the double bonds and you introduce 6 chlorine atoms in the benzene ring, then it will become gamaxine and it is called hexachlorobenzene. BHC also it is called benzene hexachloride. So, this type of material can be prepared, can be synthesized from benzene and chlorine by gamma ray irradiation. It is sometimes it is done by UV light also, but gamma rays also can do the same way. So, gamaxine can be produced. So, this is an application. Okay. Now, formation of ethyl bromide, ethyl bromide C2H5Br, you can produce this from ethane and HBr. So, if you take a mixture of ethane and HBr, it is some type of addition reaction, there is a double bond. So, in the double bond that HBr is added up to form this one. So, how it is done? You take mixture and then you irradiate it with gamma rays. Okay. Then this ethyl bromide will be formed. There are many other reactions, I have picked up only few. Now, these are some of the uses. Some uses of isotopes. This is not radioisotope. The application is this application of isotope. Okay. Now, this is a very important reaction. This is the photosynthesis. Photosynthesis. Here 6 CO2 plus 6 water gives C6H12O6, one molecule the glucose and then 6 oxygen, 6 molecules of oxygen. Now, for this one question may come to your mind. Okay, oxygen is produced, but this oxygen is coming from carbon dioxide or it is coming from water. Okay. This is very important question. Now, oxygen that produced oxygen is coming, this oxygen is this oxygen or this oxygen. So, mechanism, actually it is a mechanism to study the reaction mechanism. This for this work means to know the mechanism, Nobel Prize to Calvin and co-workers was given, 1961 Nobel Prize was given. It can be done by isotopic leveling. Isotopic leveling means this isotope of oxygen, oxygen is actually 16,8, but it is 18,8. So, it is an isotope of oxygen. Now, if you label, say for example, this oxygen, you take water with this oxygen O18, okay, and then you allow the reaction to go on, then if you see that this oxygen contains the O18, then you will understand that this oxygen is coming from here. Okay. So, and if you see that there is no O18, even if you use this water labeled with O18, then you will understand that this oxygen is coming from here. So, this experiment is called isotopic labeling, isotopic labeling. Okay. Interesting experiment. Now, here another, you have already learned this esterification and ester hydrolysis. Okay. This is the esterification from a carboxylic acid RCOOH and some alcohol R dash OH, you are preparing the ester RCOO R dash plus water. Okay. Now, question is whether in the water this OH or this OH. So, this also can be done by isotopic labeling. So, for example, you label this oxygen as O18 and then you find out this water, that is produced water, whether it contains the O18 or not. If you see that this contains O18, then this OH is forming the water. But if you see that there is no O18, then this is coming here. Okay. So, but actually what is the mechanism here, depending on the, both can happen, this OH can be this OH or it can be this OH, both are possible depending on the carboxylic acid, this combination carboxylic acid and alcohol. It is not always true that this OH is coming from here, it may come from here also, depending on what acid you are taking and what alcohol you are taking. Okay. But this method is called isotopic labeling. Here it is not radioisotope, but it is isotope. Okay. Now, analytical chemistry also you can use this, here it is radioisotope, okay. Iodine 131. So, silver ion determination, estimation, you know silver, I have told you in my previous modules that silver plus can be precipitated as silver chloride. If you add some sodium chloride, say for example, then it will be precipitated as silver chloride and you can estimate it how much silver is present. But all silver plus is not precipitated actually. So, then what you should do to know accurately, more accurately, you can do something like you can use this to know in microgram level. Actually, by doing silver chloride you can go up to milligram level determination, but here it is you can do by microgram level determination. How? Say for example, you can use Ki, say for example potassium iodide, but labeled with iodine 131. Okay, iodine 131. Now, iodine 131 you can add here to form the silver iodide, and that silver iodide you can take out. Of course, there you have to add some ferric ions to form the ferrous or ferric ions to form the hydroxide of it, so that it can be trapped easily as the precipitate, and then you can estimate. Okay. If you estimate that, then you can easily, and because you have used this iodine 131, so you can easily find out how much silver was there. Means it is a better method in terms of level of detection or level of estimation. Means you can go lower level of detection or determination. So, that is in analytical chemistry. Now, radiochromatography. Chromatography you all know. Chromatography is a method to separate things like some molecules, it can be molecules, it can be ions okay, to separate it, and then after separation there should be some detection unit, so that you can detect it. But here it is radio chromatography, it is also chromatography, but then that radioactivity is applied. Okay. How? Separation of a number of elements from their mixtures and subsequent identification by the radioactivity. That is why it is called radio chromatography. These Seaborg and co-workers, they have used this technique to separate the trans-uranium elements. Trans-uranium elements separation, they have used this technique. So, what is there? In a nutshell, you can tell that separation of a number of elements by chromatography. First chromatographic technique, and then when it is eluted, you know, so in the chromatography what we do, we first adsorb it in some adsorbing column, and then we elute it with solvents, and the things which is present in the mixture, they come out one by one, okay, and then we detect it and determine it. So, here when they are eluted by something, you can use many things for elution. After that, identification of the elements by the radioactivity is done, and a plot of activity against volume of eluent. So, in the x axis you plot the volume of eluent, and you will get sharp peaks for the transuranium element. So, each element will give one peak, sharp peak, that way you will know what is this, and in which eluent it is coming. Okay. So, it is basically separation as well as identification. Okay. Complicated, not complicated, means mechanism is same, but in the normal chromatography we either use some UV visible method or other methods, but here it is radioactivity. Okay. Radioactivity property is used. Now, this is also another type of another application. Now, industrial use, what is the industrial use? You know, thickness of sheets moving on a conveyor belt. You have seen conveyor belt in the airports and many places, shopping malls. So, conveyor belt, thickness of the sheets, it is decayed after some time, it goes means thickness goes thickness becomes less. So, to know this, what it is done is measured by placing thickness of the sheets moving on a conveyor belt is measured. Thickness is measured by placing, this is strontium 90, this is beta emitter, it is radioactive, okay, it gives beta rays, okay, under the belt, and measuring the activity using a detector. So, there is some instrument by which you can see you can detect the radioactivity, okay, and then you will know the thickness. So, that is the concept. Now, medicinal use, radioactive iodine 131 for thyroid gland disorder. So, some sodium iodide, say for example, is pushed and then it goes to the thyroid gland, and there it is radioactive. So, it means it cures the disorder. Okay. Radioactive iodine is a beta emitter. The radiation destroys the malignant cells without affecting the normal cells. It will preferentially go to the thyroid gland. Okay. Iodine, na? So, it will go to the thyroid gland, and then there it will because it is radioactive. So, it will give out the beta rays, and then the malignant cells will be killed, but normal cells will not be killed. Now, gamma ray from cobalt 60, cobalt 60 is a gamma ray emitter. So, gamma rays coming out, it can be used for cancer treatment. So, gamma rays are used for cancer treatment. This is also application. Now, this is sodium chloride solution labeled with sodium 24, it is also beta ray emitter. So, what it is done, why it is used? To identify any abnormality in circulation of blood. Circulation of blood, whether there is some abnormality in the circulation of blood, it can be identified. How sodium chloride solution, where the sodium 24 is applied, which is radioactive. So, that is injected in the veins. Okay. After that, if the system is normal, then you should see the activity within 1 hour. You can see the activity in your feet, okay, in the feet, but if there is some abnormality, it will take longer time to identify, to recognize the activity in your feet. Okay. So, that way you will understand, okay, this is normal, your blood circulation is normal, or it is or it is some abnormality is there. So, that is the all those things are medicinal use. So, there are lot of use for those types of radiations. Okay. So, this is some uses of isotopes, some radiation and radioactive isotopes also we have shown. So, radioactivity has lot of applications. Now, measurement, you can tell me how the radioactivity is measured. Radioactivity we cannot see it, right. So, how we can measure it, how we will know that this is radioactive. Okay. So, there are many methods. How radioactivity is measured based on the following properties. They have some property, you have seen the alpha ray have some property, beta ray have some property, gamma also some property. So, based on those properties the measurements can be done. One property is what? Radioactive radiations can affect photographic plates, that we have already seen in the discovery. You know that exposed, the photographic plates were exposed, okay, by the radiations. So, by using this you can know that, okay, in fact they also speculated from the in the same way that, okay, there is something in the bottle, that is potassium uranyl sulphate, that is giving something radiations that is exposing the photographic plate. Okay. But now why it is happening? Because you know now we are doing all the photography, that classical photography is gone now. Now we are all digital. Okay. But what is the mechanism? This is very nice chemistry is there in the classical photography. What is there in the photographic film or photographic plate? That is nothing but silver bromide, and when the light is coming in the silver bromide, it is producing silver 0. Silver 0 means silver 0 oxidation state, silver 0, and that will produce spots, black spots, and that will see the producing the latent image, black dots it will produce. It is a very nice science, chemistry actually. But this way also, when the light is passing, means radioactive rays are passing, some rays are passing there, and then photographic plates are exposed. Okay. And you cannot stop it by putting any aluminum foil, or by putting any black paper, or by putting some wood, nothing will block this rays. Okay. That thing happened there with Becquerel first time. The another property of radioactive radiation is that it can ionize the gas. It can ionize a gas. So, you will see, I will show you Goldtip electroscope and Geiger-Müller counter. These two are the instruments that by which you can detect or measure the radioactivity, that I will show you later. Another property is radioactive radiations can produce luminescence in substances such as zinc sulphide. This property is most prominent with alpha rays. Okay. It produces bright flash and it can be seen in the dark room with a telescope. Okay. The counted flashes provide the measure of the radiation. So, there is the screen where zinc sulphide is there. Then when these types of rays are coming, then they will produce on the screen, they will produce flash, okay, bright flash, and if you make the room dark, then you can see the flash, okay, and these are nothing but the radioactive radiations. So, this is a property, okay, and by which how many flashes are coming, by which by that you can tell that, okay, how many radiations, how many particles are coming like this. So, this is one method. Another method is there, this is the radioactive radiations, that I will show you the things. Okay. Goldtip electroscope, this is very old thing. Becquerel and Madame Curie, they have used this thing actually. The you know, these are the thin foils of gold, and this is the rod. Okay, this is insulated. Okay, and there is some air also, but here it is a plate, metal. This is metal rod. Okay, metal rod, and this is the some plate. Okay, if you keep some charge here, then charge will go here, and then this two plates, the leaves, they are called leaves, gold, actually made of gold, fine, very fine leaves are there. These leaves, because the charge is similar, so they will repel each other. Okay, and they will go like this. But if you bring some radioactive element here, and they will produce some radiations, and then the air, they will ionize the air. Okay, when the air will be ionized, so this one will discharge their charge there in the ionized air, and then they will come like this. They will not repel anymore, they will come like this. So this is the by this way they will know that okay, radioactivity is coming from the element. Okay. So this is a old type, but here it is the Geiger-Müller counter, Geiger-Müller tube or Geiger-Müller counter you can use. Here argon gas is there, and there is the, this is a tube, okay, metal tube actually, and this is connected, this is the negative electrode, and this is insulated, and this is a wire, metal wire, this is the positive. Okay, this is joined, and high voltage is passed. Now when the beta rays are coming, say for example, then here there is the argon gas. Okay, argon gas is there, so it will ionize the gas, and it will produce positive argons, and then electrons and positive argon gas. Then these electrons will be discharged here, because it is electrons will be discharged here and positive argons will be discharged here. Then you will see some sound, you will listen to some sounds. Okay, so it will be discharged, so you will see some sound. So kit 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 like this. So you will from there you will know how much radioactivity is there. A portable type, you can take it from here to there, and you can put it somewhere to know whether it is, there is some radioactivity in some material or not, handy things, and you can count also. So these are the two things. There are other things also, but these are the two things that you can use for measurement and detection of radioactivity. Now, so radioactivity is very important. No? It has many applications and very interesting properties. Although you have to be very careful when you are using this type of radioactive elements, you have to be very careful, because they can create cancer, they can they are health, they produce health hazard also. So that is why you have to be very careful. There are some special dresses also, special goggles also, special equipment, special arrangement also to protect us from this type of radioactive radiations. Okay. These same three books I can refer for this this chapter, and in this lecture we have discussed about the radiocarbon dating, very interesting radiocarbon dating, some applications of radioactive radiations and isotopes, measurements of radioactivity, how we can do, that is also described. Thank you very much.